Exercise 15. Solid lithium hydroxide is used in spaced vehicles to remove exhaled carbon dioxide from the living environment by forming solid lithium carbonate and liquid water. What mass of gaseous carbon dioxide can be absorbed by 1 kilogram of lithium hydroxide? So I'm hoping that you can pretty easily use the factor label method to answer this problem. But since we just introduced this table math idea, let's do that. Okay, so we have solid lithium hydroxide. So lithium hydroxide. Oh, it's removing carbon dioxide, right? That's the whole point. It reacts with the carbon dioxide to remove it, and it forms solid lithium carbonate. Lithium carbonate. Let's see. Carbonate's a -2. Lithium's only a +1, so I'll have to make those charges balance. And water. So there is my unbalanced equation. So let's balance it real quick. Let's start with this complicated looking thing. I have 1 lithium here, 2 right there. So let's try sticking a 2 in front of there. So my lithiums are balanced. Let's try my oxygens. And notice I don't have any pure elements, so I'm not even going to bother with that. But if I get stuck, I'll try to double everything. So oxygens. Oh, so I got 1 there, 2 more there, so that's 3. No, 2 there, sorry, because I have 2 plus 2 more, that's 4. I have 3, 4 on this side, 3. Oh, but I have this one right here, so I have 4 on this side, 4 on this side. Oxygens are good. What about my hydrogens? I have 2 hydrogens there, 2 hydrogens there, so those are balanced. How about my carbons would be my last one. 1 right there, 1 right there. Looks like this equation is already balanced with the ratio of 2 to 1 to 1 to 1. So that's a 2 to 1 to 1 to 1. But before I start getting into calculations, I'm going to need some molar masses. Now, you guys know how to work a calculator. I kind of happen to know where these are off the top of my head because I've done problems with these quite a bit. So I'm just going to knock these out. You just have to trust me that these are the correct molar masses. Or I guess you don't have to trust me. You could just do it in your calculator right now just to prove it to yourself. But notice I have the species, a balanced equation, mole to mole ratios, and molar masses to work with. With the addition of Avogadro's number and standard molar volume, I can use the entirety of the mole map at any point. Now, in this problem, we are, let's see, observed by 1 kilogram of lithium hydroxide. So this stuff, right? This stuff. So I have 1,000 grams. I'm going to go ahead and put this into grams because my molar mass conversion factor is grams per mole, not kilograms per mole. And a kili means 1,000, so it's 1 kilogram. It's 1,000 grams. So for every 1,000 grams, what is the mass of carbon dioxide? This column right here. Now, in order to go from mass to a mass, I'm going to have to go through moles and then back down to a mass. So how many moles is this? How many moles is this? So I have this many grams. This is the molar mass. What is the amount of moles present? 1,000 divided by 23.95. I have 41. Let's call that 75 moles. Right? Again, if you don't trust me, see that I did division here. I did division right there. Well, from the mass, 2 moles, I went against the arrow, so I divided by the molar mass. Divided by the molar mass. Alright, now that I have the amount of moles here, right, on lithium oxide, I know that it's a 2-to-1 ratio, so this value is going to be half this. So, divide by 2. So, let's go. What am I going to round that to? 20 point. How many significant figures am I using here?
I guess I'm limited by 3, really.
Just go 3.
Get back on there. So that'll be 20.9.
Yeah.
20.9. So, when I have a kilogram of lithium hydroxide, there are 41.75 moles of lithium hydroxide.
I guess maybe I should just wrote this as an 8 and not a 5.
41.8 moles. 41.8 moles of lithium hydroxide. There are twice as many moles, you can see that from this ratio here, there are twice as many moles of lithium hydroxide as there are carbon dioxide, so I half the molar amount. And now I'm going to multiply the number of moles by the molar mass
to get the mass of the carbon dioxide.
Let's see. Again, 3 significant figures.
So what does that tell me to do? 919?
Of CO2?
I think that looks good.
Actually, see 920. Well, no, that's still fine. There's always this question that
I would get in Gen Chem, and I'll probably get it more this year.
the question is,
How come this answer isn't the exact same as this one?
my response is that it is. The AP instructors are instructed to use 2 ideas when considering final answers. One is you get 1 decimal place in terms of significant figures. That means you can be off by 1 in terms of your number of significant figures. That's kind of lucky for you. That's pretty good. That should be not a problem. You can also be off by 1 value, okay, a value of 1. So for this example, let's say the AP graders, the answer that they have written down that they're grading towards is 920, like it is here. And you write 919, full credit. Full credit. If you would have written 921, full credit. 919.5, you know, an extra significant figure, full credit. That's generally what the AP graders are looking at here.
Let me
just double check something to see if we can figure out where that
that 1 value disappeared to.
So because I incorrectly said this should have only had 3 significant figures, but I kept all that in there.
What if I went 41.8 divided by 2?
No, that didn't be the exact same. But I would still get full credit, so hopefully you can take my word for that one.